So, ladies and gentlemen, welcome to the conference. From space, we see it better, what remote sensing can tell us about Earth, organized here by the Embassy of Brazil in Berlin. This conference is, as you can see, part of the Berlin Science Week, which is taking place between November 1st and November 10th. This is a hybrid event, meaning that we are accompanied both by the audience here in the embassy, but also audience online. We have a very exciting program today, which is comprised of two panels and one presentation. The first panel will address remote sensing of water and soil. And the second is about the subject remote sensing of plants and forests. The event will be closed with a presentation on the evolution of remote sensing since the 1970s and contributions from Brazil. For those present here at the embassy, wine and snacks will be provided in the hall next door after the event. To start our agenda, I have the honor to call up on stage His Excellency, Mr. Roberto Jaguaribe, the Ambassador of Brazil to Germany.
Well, good afternoon, and dear friends, ladies and gentlemen present here in the embassy, and also those connected online. I'm very pleased to welcome you to the conference. From space, we see it better. What remote sensing can tell us about Earth. I would like to greet Cláudia Guimarães Steinecke, Evelyn Leão Moraes Novo, Albi Duarte Rocha, Gabriel Medeiros Abraão, Igor Ogashuara, Wanderson de Souza Mendes, who are going to be in the panels today, and of course, Pedro Ivo Ferraz da Silva, who just spoke, and who's the head of our Science and Technology Department at the Embassy, and who enabled all of this for us today. I'm very grateful also to the organizers of the Berlin Science Week for the excellent program and list of speakers this year. We are glad to be able to contribute to this celebration of science. And this year we are hosting this event on remote sensing and its great diversity of applications. And of course, it shouldn't be a surprise to you that Brazil is very interesting in this topic and that we are hosting this event today because Brazil is a very, very large country, 8.5 million square kilometers, about twice the size of the European Union. And we need remote sensing to deal with many of the different challenges that we have in the country. And of course, given all of these challenges and the opportunities associated with them, we have developed some capability to deal with this issue, which I hope you will witness in the presentations today. And of course, this is the strategic technology for Brazil. We deploy remote sensing for many different purposes: weather forecasting, border monitoring, estimation of agricultural produce, impact assessment of climate change, wildfire warning systems, monitoring of water bodies, and of course, many others that we will hear from today. Professor Evelyn Novo, who is joining us from São José dos Campos in the state of São Paulo this afternoon, represents the leading Brazilian institution in this domain. The National Institute of Space Research, founded more than 50 years ago, is internationally renowned for its applications to monitor deforestation in the Brazilian biomes, among many others. The program for monitoring the Brazilian Amazon rainforest by satellite and the real-time deforestation detection system are known for being precise and trustful. Both provide essential data for governmental institutions, law enforcement agencies, civil society organizations, and academia. These inputs have been key to the development of public policies and environmental norms, such as the one of its kind Forest Code in Brazil, enacted in 2012. INPE, the short name for the Institute, has also made an essential contribution to data access. The website Terra Brasilis available both in Portuguese and in English, displays through intuitive maps and dashboards the data gathered by the mentioned for deforestation monitoring programs. And of course, it's very interesting to follow. The Brazilian capacity in remote sensing is enhanced by other institutions such as the Brazilian Agricultural Research Corporation, the National Institute of Amazonian Research, and various different public universities. More recently, a dynamic ecosystem of startups, especially agritechs, has emerged, combining satellite images with artificial intelligence. These Brazilian companies have been developing innovative solutions to assess soil quality, estimate yields, and advise on the use of inputs such as fertilizers and pesticides. In a nutshell, Brazil is both a technological powerhouse and a rich deployment laboratory for remote sensing. I'm sure you will get the feeling of this while listening to our guests today. Talking about our guests, I would like to stress that this event would not have been possible without the fundamental support of Dr. Igor Ogashwara, who is currently a postdoctoral researcher in the Leibniz Institute of Freshwater Ecology and Inland Fisheries here in Germany. Dr. Ogashwara has a central role in conceiving the program and indicating the panelists. Our special thanks to him and also to the researchers who have accepted our invitation. The panelists present here in the embassy today are members of the Brazilian diaspora in science and technology in Germany. As you could probably identify in the program, they all conduct research in top-notch German institutions in various fields of knowledge: hydrology, climate, botany, agriculture. At the beginning of 2021, the Brazilian embassy in Berlin and Pedro have organized the first meeting of the Brazilian Science and Innovation Diaspora in Germany as a kickoff event for mobilizing Brazilian researchers in Germany. There are more than 500 of them in all branches of science, physical sciences, life sciences, social sciences, and in all 16 German Länder states. We want to encourage the establishment of a network of Brazilian researchers in Germany in order to foster professional and personal ties and to pursue common interests and to exchange experiences. The Apoena Network, that is the name that they have given to the network, was founded in the beginning of this year and has already been very active. I encourage all of you to engage with them as they are becoming instrumental to deepen German-Brazilian scientific ties. We are convinced that diaspora members can be very effective in building bridges between the institution they work for here in Germany and the Brazilian research landscape. Being experienced in both German and Brazilian scientific innovation cultures, they are uniquely positioned to identify complementarities and explore cooperation opportunities between both countries. In order to leverage this great potential, the Brazilian Embassy have been disseminating information about the bilateral funding opportunities and promoting matchmaking events between the diaspora and Brazilian institutions. I hope you can take the opportunity today to begin networking with our panelists and among yourselves and eventually explore the avenue of collaboration. I wish you all a very successful event. Thank you very much.
Thank you very much for your words, Ambassador. We will now proceed to the panel Remote Sensing of Water and Soil. And I have the pleasure to invite up on stage Dr. Gabriel Medeiros Abraão of the Potsdam Institute for Climate Impact Research, PIK. Dr. Igor Ogashwara, as the ambassador said, of the Leibniz Institute of Freshwater Ecology and Inland Fisheries, IGB, and Dr. Wanderson de Souza Mendes of the Leibniz Center for Agricultural Landscape Research, SALF. We will listen to the three presentations, and afterwards there will be time for questions from the audience. First, let us hear Dr. Gabriel Abraão with the presentation Amazon Hydrology from Space, Scientific Advances and Future Challenges. Dr. Abraão is a postdoc researcher at PIK. He took his bachelor in agricultural and environmental engineering and his doctorate in applied meteorology from the Federal University of Viçosa in Brazil. His main research topics are related to interactions in the climate, land, energy, water nexus. Gabriel, the floor is yours.
Thank you. My name is Gabriel Abraham. I'm the postdoc researcher at PIC. And does this thing work here? Or? I think should it? It's off. Sorry. Given that maybe not all of you are familiar with the topic, I'd like to kick off some great presentations today with a broad overview of a place where seeing things from space is very important, which is the Amazon Basin. I'll be giving out some selected examples of a very large review we just conducted on the Amazon hydrology and remote sensing. That's set to become a book very soon. So if you're interested in the theme, keep posted. That it's going to be free and accessible for all. So why the Amazon Basin? So the Amazon Basin is the world's largest hydrological system. It's very hard to even comprehend its dimension from the soil. It just charges 200,000 square meters of water per second into the ocean. That's about 5,000 the River Spree that's outside here. And it's a very large area and a very diverse area. I can't see what I've written there, actually, but it's a very diverse area with mountains, plains that are ever changing because of the river dynamics, because of all the water. It's subject to a lot of human pressure. It spans the jurisdictions of 8 different countries. So it's basically So it's basically an ideal laboratory for remote sensing because first, all the things that happen there are big. All the vegetation patches are big, the rivers are very big, and so it's relatively easy to see from space, and it's very hard to see from the surface. So a lot of the things we know about the Amazon Basin, we know because of the existence of remote sensing itself. What happened is that these remote sensing techniques, especially in terms of vegetation and water in the Amazon Basin, they co-evoluted with one another. A lot of techniques were developed for the Amazon Basin, and several techniques that are used in other places were developed at the Amazon Basin, precisely because of the challenges. So to give some examples of what we can see, so the place is so large that we didn't even know what the river network was like before we could actually see it from space. That's in the early 2000s. That's the. Does this have a laser? No? Yeah. Yeah. Well, so we needed to have satellite images to even understand how the river network used. We can't even gauge the water level at as many places as we'd like. And today we do that also with remote sensing. We have several virtual networks of observations, as we call them, that observe the water level at the most remote regions. We didn't know what the topography itself looked like because we couldn't see below the water, and we couldn't survey all these rivers. So, but I'm going to save most of the history lesson for Professor Novo at the end, which was part of all this. But there are some things that are a little less obvious that we can see from space view. So for example, today we have satellites that can detect small, very small variations in the Earth's gravity field. And with that, since most of what changes in mass and the surface is actually water moving from one place to the other, from the atmosphere to the ground, we can actually measure how much water is in underground and above ground and how it changes over time with a surprisingly fine spatial resolution thanks to remote sensing. We can also see rainfall because that's another thing we can't really measure over such a big place such as the Amazon. And we have weather radars and a whole constellation of satellites today that are dedicated to seeing precipitation from the space. And we found out after we could finally see this from the outside, we saw that some of the places that rained the most in the basin, we didn't even know it rained so much there because we didn't have rain gauges there. And we can even see the composition of the atmospheric water. So one of the more recent developments is that we can see different hydrogen isotopes on the atmosphere. And we can, with that, so since the water, so basically the water that evaporates from a surface, it's lighter than the water that transpirates from a plant. So we can essentially map how much of the water in the atmosphere comes from plants or comes from free water. And with that, we could have some very important advancements in the comprehension of how the rainy season started in the Amazon and the role of the forest itself, since a lot of the water that is there at the start of the rainy season actually comes from the forest, from last year's rain. Sorry. Of course, we'll have more people talking about this later, but we can also see the land and the aquatic vegetation. The remote sensing of the vegetation in the Amazon was actually one of the reasons why we have satellite data to begin with. But again, that's something for Professor Evelyn later. And we can also see the vegetation that is in the water. And by crossing all this information, which I believe is are the most important applications, we can start seeing how human activities impacted the hydrology of the Amazon basin. Another recent developments are the impacts of deforestation on rainfall. So we could find, with all this fine data on both precipitation and the land cover, so we know we can match these two, and we could decipher some of the effects of the deforestation on rainfall and find out that indeed cutting down trees reduces how much it rains, and it substantially reduces how long it rains, so it really shortens the rainy season in the Amazon. And some very interesting complex patterns that happen in the state of Rondônia especially, and in relatively small clearings where people had the impression that deforesting actually increased rainfall. So we found out that, yes, that is indeed true, but only if you deforest just a few hectares at a time. And if you deforest too much, then it's just bad. We'd also learn more on the impacts of dams. We know that the construction of dams, the flood dynamics affects the seasonal variation of rivers, and also changes the amount of sediment in the water. So the sediments that are afloat on the rivers, they precipitate before in the dam, and then they don't go to the rest of the river. A little more on why that is important later. And we found out that some dam projects have massive mortality, that led to massive mortality of trees on the Amazon floodplains, and that this sediment effect was also very large in terms of how much sediment is transported downriver. And just to give one example where this is actually very relevant, I'm sorry, this thing is a little slow. I end up putting it to. We could document really a one of a kind phenomenon, which was the death of the Pororoca. Those who don't know, the Pororoca is this phenomenon where the rivers are very when the river meets the sea. So the lowlands are very flat, and there's a lot of water from the rivers, and there's a lot of influence from the tides, which ends up creating waves that can be surfed, or at least could be surfed, especially in this place, the Araguari River, which is it's not a tributary of the Amazon, or at least it wasn't. It was a river in the Amazon basin that would drain to the sea, and it was the place where the Pororoca would happen the most. And it's a very large river. As you can see, that's 2,000 square meters per second. It's very tiny, close to the Amazon, but it's very big. It's still like 50 sprays, I guess. And in the 2000s, a couple of things came together. One were the dams that I mentioned that wouldn't let the sediments from upriver to deposit in the lowlands with the same rate as they used to. And the other was some intensive buffalo farming that happened in this region. I can't point here, but in this region between the two rivers. So the Araguari is the one on the top, and the Amazon is on the bottom. And this all this combined with the crazy flood dynamics that happened there created a channel that grew from the Amazon River towards the Araguari River, which is also something that has never been seen before. And in the end, all that water was captured by the Amazon, and now the Araguari River, it's basically gone. There's almost no water there anymore. So in conclusion, so this is just an overview of what the remote sensing done for the Amazon basin hydrology. There will be, I believe, more important updates late. So it led to very important scientific discoveries, and it's a model of how remote sensing can be used for governance. But we found out there's a lot of existing science that still could be applied to improve the lives of those on the Amazon. We still don't have, for example, a system to monitor droughts and floods that created a humanitarian crisis a couple of years ago, for example, and it was totally predictable. We could be seeing that. We don't use this really on the development of new hydropower projects. We could be using this to monitor mining activity. So there's a lot of science, but there's still a lot that can be done to use that science to improving people's lives there. And that's it. Thank you.
Gabriel, thank you very much. We will now proceed with the presentation of Dr. Igor Ogashvara. Igor, the floor is yours.
Thank you, Pedro. So, good afternoon, everyone. So, I will talk today about how we can monitor water quality from space. Can you pass to the another one, please? So, how can we monitor? Can you pass another one? So, to start, how it works. So, how can we use satellite imagery to monitor water quality? What we do, we use passive remote sensing, which means we depend on sunlight. So all the sunlight interacts with the water body, for example, on a lake, and the light penetrates in the lake and will interact with algae, with organic matter, with sediments. Some of this light will be absorbed by these particles, some will be backscattered going back to the satellite. And then we can evaluate what is coming out of the lake and measure water quality parameters. Next one, please. So how it works. So the satellite will see more or less this spectrum that we have on the picture. So we see different water colors we will generate different type of spectra, different types of reflectance. And based on these different signatures of the reflectance, we can quantify different parameters. For example, chlorophyll A, that represents algae, CDUM, colored solvent organic matter, that is organic matter, and total suspended solids, for example. Next one, please. But when we do remote sensing, we do not only stay in front of the computer, getting the satellite image in the computer. We also need to go a lot to the field. So we go to the field, we collect data, in situ data, radiometric data. We also collect water samples, go to the lab, analyze all the water samples. Next one, please. And all this information we try to aggregate. So we are collecting radiometric data in the rivers, in the lakes. We are getting water quality data. We are getting satellite data, and we put everything together in an algorithm or in a model, and then we can estimate water quality parameters. Next one, please. So why should we use satellite images? Next one. One way to why we should use satellite images is to identify spatial patterns. So usually traditional, when we do monitor a lake, you usually go to the boat with the boat to one single point in the lake, usually in the middle of the lake, collect a water sample and go back to the lab. But with the satellites, we can see the entire lake. So sometimes we will miss a point in the lake. So when we are only trusting in one single point in the lake to collect our water samples and represent the whole lake, it's not possible. So satellites will help us to see the spatial. Next one, please. Another one is to identify temporal patterns. So in this case here is a Barra Bonita Reservoir in countryside São Paulo State. And with the satellite data, we can build a time series. So we can collect data a lot of times, and then we can create a time series, or temporally we see how, for example, an algae bloom is developing in a reservoir, in a lake, in a river. Next one, please. The other thing is to see what we do not monitor. So sometimes we cannot cover all lakes. For example, this is an image from the Mecklenburg-Vorpommern Lake District. And there's a lot of lakes. So we cannot cover all of those, monitoring it by lake, by boat. So sometimes you can see what we don't see. So if you can click another one. Yeah, so for example, this case, there is a small lake, Kleiner Glitzensee, that is very close to the Leibniz Institute. And in the satellite image, it was showing very red. But since we do not monitor, we didn't know that something was going on there. And when we saw it on the satellite image, then we decided to go there, and what we saw was a bloom of algae. Next one, please. So how can we use satellite imagery for our daily life? Next one, please. So one case that was very important, for example, was the River Oder case. So it happens in 2 months ago in August in the River Oder, which is between Germany and Poland. And there was a big death of fish caused by some algotoxins. And how remote sensing or satellite image could help with that. Next one, please. So satellite imagery could identify that the algae bloom was coming up. So if we had operational monitoring system using satellite images, we could try to prevent this case, or at least we would know that the river Oder poisoning algae was coming up. Next one, please. Another case is to forecast blooms. So this is an example from Lake Erie in the US. And with satellite data looking on algae blooms and based on the hydrodynamics or wind, we can forecast where the blooms will go. So if it's a harmful algae bloom, then we have to close all the lake area. Next one, please. So take-home messages. So remote sensing of inland water is a very, very new topic. So if you see in this graph, most of the research, most of the publications were done in the last 10 years. So this everything is still under developing. So satellite images can help us to observe all these spatial dynamics, but we are still developing models, we are still developing algorithms, and we are still developing new satellites. So there are a lot of new satellites that are coming up, and they will help us to monitor more and more parameters of water quality. And to finalize, more in situ data is also needed. So we also need to collect more data, especially data that match up the satellite passages. Next one. So I would like to thank everyone for your attention today, and hope to answer your questions during the discussion.
I just realized I made a grave mistake, which was not to introduce Igor properly. So, as the saying goes, better late than never. Igor, as you know, is the postdoc of IGB, but he's also a visiting professor at Universidad de Concepción in Chile. He got his bachelor in geography from the State University of São Paulo, his master from the Brazilian National Institute for Space Research, and his PhD from Indiana University in the US. So now we move to Wanderson, who will deliver a presentation on soil sensing and landscape modeling for soil health in time of climate change. Wanderson works as a postdoc researcher at ZALF. He started to work with remote and proximal sensing during his bachelor in agricultural engineering, and he got his PhD at the Luiz de Queiroz College of Agriculture, ESALC, of the University of São Paulo, with the project Geotechnologies Applied in Digital Soil Mapping. Wanderson, the floor is yours.
Let's see. Everyone can hear me, right? I'll make a little bit different. So the intention, yeah, perfect. The intention today is to keep that simple, right? I want to share what I have been doing since I got my PhD, and what was the intention that myself and my colleagues are really passionate about science and specifically remote and proximal sensing. Can you press the next one, please? Yeah, perfect. So as you can see it, like that's why first slide actually I like to put some photos of what we do. Can you move on? Back. One more. Yeah. So what is remote or soil or proximal sensing? Have everyone here heard about it or familiar with the topic? Can you just show your hands? Yeah. Not all of you, right? Imagine like a picture when you use your phone. When you take like a panoramic photo, that's what would be remote sensing. You have like the big picture, but you don't catch the detailed information. When you move close to the object, when you take photo, for example, of your hand or close to your hand, you see the small details and really high resolution detail information you have in your hands, as I'm showing this example, right? So it's basically what we play with, but with soil, which everyone here can define that in a different way. You can say that's the body you grow plants and you just walk on, but it's more than that. That's the main part of the mitigation process that we face in these tough times of climate change. And the global temperatures has been increasing drastically in the last couple of decades. And what is the soil in this main picture? There's these three major biogenic and anthropogenic greenhouse gas emissions that we are familiar with, right? Carbon dioxide, methane, and nitrous oxide. Those are the three main ones. And as we see it, land use is responsible for approximately 25% of what we putting out in the atmosphere, right? So agriculture and deforestation are the main um, drivers of this process. So what we can do using remote sensing, proximal sensing to preserve ecosystem like peatlands we have in Germany. I'm working with degraded peatlands, which is like perfect for agriculture because we have the high level of soil fertile soils in this kind of ecosystems. In forests, because there we can, capture the CO2 and it's part of the entire process. And I've seen it as much as we increase this degradation, we have these natural disasters going on in the planet, and even each year getting worse. So it's a nature. Nature looks for balance, and balance is part of this entire cycle and process. And that's where we rely on it. The science technology, the guys that we sometimes imagine that was just behind the desks, where we go to the field and try to bring new methodologies and insights that can improve what we know about soils, what we know about the environment itself, and how can we actually try to recover on the damage we have been causing so far. And through this process, that's where we use remote sensing to come with new practice, implementing new systems, or come with like restoring new areas with forest and implementing systems that can improve the soil itself to store carbon and nitrogen, part of this biogeochemical dynamics we have in climate change, and comes to the end of this process. That's implementation. And the implementation is the end that everyone see it. When policymakers comes with new laws or fundings or give us the opportunity to make the difference. And now through this entire process, we have the European Union Commission giving fundings and providing service that we can integrate this entire system. From what we develop in science, implementing the practice in field that farmers are definitely doing it, what they can do to keep production. We don't need new areas. We don't need to, create a space for agriculture. We can use the areas, and as I'll try to show you really quickly through it. I have been working with tropical soils. So basically, as you see in the red dots, it's like a farm level that we call it. We have the soil information at farm scale, but you could ask, how can we extrapolate that information? How can I know in the areas that's not on the red dot about the soil? And then that's when we use the remote sense information with machine learn, artificial intelligence, names that you probably have heard, to get this main picture of the areas that I don't know what is there. By using remote sensing, proximal sensing, based on the areas that I know the information, I can kind of, like we say, predict. I can know what is going on in the areas that there is no information. And what's the main goal? For example, in the study, this study area, we had like 47% just used for sugarcane production, which give like just numbers, as you've seen on the screen. It's a huge system in that specific area. So what is about this yield environment? What you see in green is that you can, like the inputs you have in the area, you can produce more. In the areas that you see this pink colors, low level production, it doesn't matter. You cannot go there and add more fertilizers. You won't produce more because that's the limitation the soil have in that region, right? You have different soil types, so you don't explore that. So that's the main picture we provide for policymakers in the end. And this actually is a free farmers and policymakers. That region has free access to that information that we generate in the end. Moving to Germany here, that's where I'm working in peatlands. degraded peatlands. As you see on the figure, on the bottom, on your left, it's approximately 1 square kilometer, right? And when you map 20 times I red square, right? So this given the picture I have on soil organic carbon stocks. So you can see it. You move to the next one, please. You can see it the entire picture. Where I can store more carbon? Why peatlands are important? Why I should come with a better soil management on the areas? Because that's the importance of it. We're storing carbon in small environments. And it doesn't mean that you can pollute more because we have soil can store more. No, it's the other way around. You have to work to reach that balance, and you're not in the balance or even close to the balance. So it's a long-term project. But moving to worldwide, this is time series we did. It's a global project I was involved with, and as you see, just show the bare areas we have across the globe. We use the satellite image from Landsat, which is retrieved from NASA, and we developed a methodology that would capture the bare soil area from 1984 to 2020. As you see in Australia, this is a project that we published in Nature, and that's we see it Australia, Brazil, United States, Africa, European Union. That's huge, and we need to take a deep look on it and preserve what we have when we're still having it. So based on that, that comes the collaboration we have. I'm Brazilian. I'm actually working from the German side, so inviting scientists from there to work with us here. So we share the knowledge. I share the knowledge about the soil science we have here, and that's the bridge we build, working in these three different climates we have. And this T80 project that built this bridge with the main organizations in Brazil. And they will come in the following next years. So we'll be exchange knowledge and hopefully, come with something new for both sides. That's all. Sorry if I didn't get through everything, but yeah, thanks for your attention.
Wanderson, thank you very much. So we have some time for Q&A. If you want to pose questions, please raise your hand and the microphone will come to you. Any questions? There we have first one.
Hello. Thanks for the talks. It was great, all of them. I had a few questions. Hopefully they're not too technical, but the first one was for the first speaker. I'm really curious about you mentioned that you can sense now the isotope concentration from the water vapor. I never heard about this. Can you explain what satellite is it, and is it a recent technology, and do you need in situ data for it, or is it? Yes. So I had for everyone one question, one simple question. Sorry. Yes, for the second speaker. I just wanted to ask which are the most exciting new satellites that can be used for water monitoring. So, I mean, I think maybe hyperspectral, or which are the next ones you're looking at? That was my second question. And third question for third speaker. Yeah, I was curious if you learned anything about which management strategies are, like some practical insight, which management strategy are good to preserve the soil organic carbon.
I think, to be honest, I don't remember exactly the name of the satellite. It's the TES, the spectrometer aboard the Aqua, not the Modis Aqua, the new Aqua. I don't want to remember the name of the new Aqua. Yeah, I can look that up and get back to you. But it's it's a spectrometer that can go through the atmospheric column. It's like more a side look, and it's there. It's very recent. It's, I think, all the papers I've seen about it are on the Amazon, and they were all from 2018, 17. I can connect you with that.
Hi, thank you for your question. So the satellites that are coming up in 2028, there are two that are coming up in 2028. One is from NASA, is the SBG. It's Surface Biology and Geology satellite. And one from European ESA, from European Space Agency, it's called CHIME, both hyperspectral satellites. So those are the ones that we are looking for, because those will be hyperspectral satellites that will cover the whole globe.
That's one. Yeah, that's why it's important to monitor that, right? We use the proximal sense to have a good picture, and then how we can store more carbon. You use cover crops, crop rotation. And also you have to have the knowledge. It's not just working as a remote sense scientist or data scientist, but you have to have the basic knowledge of soil science, because then you use the technology in your favor. So that's a kind of transition we have, and depends on the region we work with. But definitely we find out that when you have this agroforest system, there's syntropic agriculture, permaculture, and different levels, and you can definitely store more carbon. But of course, there is a limitation for soil. Soil cannot store carbon as much as we want, or compensate the other part of the balance. You know what I mean? It's kind of like we're the generation who works for the future generation. We're trying to solve the problem that our ancestors left to us now. And yeah, it's a long run, and they're in a hurry up process.
More questions? Okay, great.
Thank you for your presentations, very interesting. I don't know a lot about satellites, so I was wondering if you all use the same satellites for the different expertise that you're doing, or do you need like a satellite for everything that you measure? Or do you need a model with the same pictures that you make that interprets the same kind of data you get from the satellite? And who owns the satellites? Like, is it companies who put it in there, or universities, or governments? Thank you. Hi, Melania from Planet. We're a company that has satellites. So. My question relates to something that you said, the last speaker said at the end, about these creation of knowledge, implementation of practices, and then turning into policy. And I was wondering, because many times to turn science into policy or into diplomacy, policymakers or decision makers shield themselves by saying that only the physical science or the natural science is known, but that we don't know enough about what intervention would lead in terms of economic or social impacts. So what kind of interdisciplinary science do you think is necessary to jump from just the purely natural science to produce the evidence that policymakers can truly utilize to make changes? Thank you.
All of you described some environmental change in your talks, and I was wondering if there's any benefits of the change that we've created from production and things like that.
So I will answer the first question. The satellite. So we all use different satellites. So there are different satellites. For example, Wanderson showed a map from Landsat. Landsat is one satellite dedicated by the name Land. Then we have other satellites like Sentinels. The Sentinel-3 is mostly for oceans. So what makes it different on the satellites is that the spectral resolution, so how many bands it can cover, so how many colors it can see, for example. And the other one is how far you can go or how small you can see it from it. So temporal and spatial resolution, that's the most important part. Other one is temporal, so how frequent we can acquire data. So that's how we kind of choose the satellites we're gonna use. Satellites, many of the satellites are from space agencies like NASA, European Space Agency, but Melania, correct me if I'm wrong, I think like Planet owns 50% of the satellites, Earth observation satellites orbiting Earth. So yeah, so there's a lot of private companies as well.
Yeah, answer your question, and glad that you asked that, and you work for Planet, right? Yeah, it's all based on the spatial resolution as well, but this interaction, and when we do science, and that's what I miss here, even working in Germany, right? Because you think you going through the entire process to see the end of this chain. There you see pharma applying new practices that can get them the same level of production they have. We cannot just build them, right? They're not. We can like share knowledge, and as you said, that's what I love it. Work with me, not for me, right? Based on that, we have this concept now in Europe called it Living Labs, which basically they're trying to connect science through the entire food chain and see what will be the end of the process. I would tell you that we work on this process, and I guess that's why I got hired here at the first place, and we're looking definitely forward to build a working group on that aspect. Come from different backgrounds, have soil scientists, have data scientists together, a social scientist, because this is really important. We have qualitative aspects that's not measured. We're just looking for numbers. Numbers are important for sure, but we need to see the quality of those. And there's other ways that you can access that. And definitely, you'll see this change in the next couple of years. That's what I think. I think that's we're getting a lot of fundings now to move through this process, and mainly interacting with the private sector as well. As you probably know, that Planet is one of the main providers. And yeah, I don't know if I answered your question, but yeah, that's my thoughts on it.
So maybe to try to answer the question about environmental changes, that's a very deep question actually, because it depends on what you consider what's a good environmental change, right? Good for who? And a lot of times we can think if it's good for nature, then we don't do a lot of good. Not that I've seen much in my career. I mean, increase the atmospheric CO2 concentrations, which can be good for some plants, but not for others. And it's always a trade-off. And in the end, we always end up looking at how these environmental changes affect humans, which I suppose is maybe the easiest way to convince us to stop changing the environment, is to show how bad it can be for us. But even there, the picture can sometimes be nuanced. Like the case of the deforestation and precipitation is a hard one, because depending on the scale, at a large scale, it's bad for everyone. But in small scale, sometimes if you deforest your property, it's good for the rainfall on your property, but it's bad for the rainfall on your neighbor's property. And it's definitely bad for timber. It's documentedly bad for crop yields on your neighbors, but you have a brand new farm to plant on. So it's really a question of justice and who this is really good for.
My question is to Gabriel. So basically, in the end of your presentation, you said that despite the advancements in remote sensing that you were able to accomplish a lot of projects and prevent, still there is a lot to go, like illegal mining and also floods and so forth. And I wanted to know what is actually preventing. Is it lack of funding? Is it technology? is it? What is preventing to expand this project that is gonna have such a beneficial impact in the Amazon?
No, that's also a complex story but I think we scientists might have something to blame too, because we normally take our jobs to develop these algorithms, find all these interesting findings, and there's a follow through that, like you were talking about how to really take these techniques and implement them in a way that helps people in the end. And it's I feel like there's a lot of connection there's a lot of connection missing in terms of policymakers and companies knowing what can be done, really, because a lot of this is very recent. So like most of what I'm showing you here, that it's not, well, everything I shown you here is from the last 20 years. A lot of it is from the last 3 or 4. So these things happen very fast. Like even in a country like Germany, like you showed, we could be preventing algal blooms, but we're not, because these things are very recent. And it takes time for things to really become policy. But of course, after these things get known, there's always political will involved, and that's always a harder story.
Great, thank you very much, Gabriel, Igor, and Wanderson. We will now stop for a 15 minutes break. Yeah, so we will be 5 minutes behind schedule. We will be back at 4:15. Thank you. We'll now proceed to the panel Remote Sensing of Plants and Forests. And I have the pleasure to invite up on stage Dr. Albi Duarte Rocha of the Technical University of Berlin. And joining us online is Dr. Claudia Guimarães Steinicke of the University of Leipzig. As in the first panel, we will listen to the presentations, and right after we'll proceed to the Q&A. So let us first hear Dr. Albi Rocha with the presentation Urban Vegetation and Evapotranspiration, Thermal Comfort Assessed by Remote Sensing. Dr. Albi Duarte Rocha is currently a research assistant at the Department of Geoinformation Processing for Landscape and Environmental Planning of TU Berlin. He holds a bachelor in statistics from the Federal University of Paraná in Brazil and a PhD in remote sensing from ITC in the Netherlands. Dr. Rocha's current research focuses on the understanding of spatiotemporal patterns in the environment using remote sensing data by modeling parameters such as vegetation, biochemical and biophysical properties, soil moisture content, and evapotranspiration. Albi, the floor is yours.
Good afternoon. So this afternoon I will speak a bit about urban vegetation and evapotranspiration. So we'll go from the more natural environment for the city. That is important too because most of the people living in cities, and with this increase in heat waves, and so we will see how we can work better our thermal comfort in the cities. Let's see. So to have a thermal comfort, we have to mitigate urban heat island. So is this process to the cities getting hot, and this is occur because the urbanization alter the water and the heat flux. Why? Because when you have one urban area, you reduce a lot the infiltration and you increase a lot of runoff of the water. So you change the balance of the water cycle, and you reduce here the evapotranspiration compared with one natural environment. But here we are speaking only about when is after the rain, and that is because the wet surfaces, there is this evaporation just after the rain or during the rain. But after this, vegetation is very important for when it's not raining too, because then you have all this process to cooling down from the latent heat flux process. That is the process of the transpiration of the plants and the evaporation of open water and the soil that cooling down the air. So if you have impervious or a ceiling surface like in the cities, you increase the surface temperature and you increase the sensible heat that you increase the temperatures. So with a green urban, you can have more thermal comfort, and you can increase evapotranspiration and evapotranspirative cooling service that is increasing the latent heat flux, and and you can have like shadows that you can increase the radiative cooling service that is blocking the radiation from the sun to reduce the temperature of surface and then reduce the sensitive heat. So let's see the difference that this occurring in a city like Berlin. So we have here one very built-up area that is near to TU Berlin in the city center. We have more residential area in Stiglitz. We have here Tempelhof Park that is basically grassland, and we have here our urban forest in more near to the borders of Berlin. So if you check how the difference of evapotranspiration and occur in these areas, you can notice that in a building area you have like annual around 130 milliliters a year. That is a kind of 22% of the rain of the average of the city. And if you have a forest, you have almost the same balance of the rain and the amount of evapotranspiration from this vegetation. So you have a huge difference. And so if you get the whole Berlin, so you can see these areas very red. That's the area that's more susceptible to have this island heat, urban heat island and heat waves. That is one of the big cause nowadays of that in Europe. And this green cooling service here is higher in these parts of more vegetation, that is these blue areas. And there are some areas like Tempelhof here that they get a good evapotranspirative cooling effect, because you have the grass that and you have the soil that transpirate, but you don't have shadows, so the surface temperature is still a bit higher. So you see here then in the radiative cooling effect is not so great. So in the average, it will be, of course, far better than the city center here, but we still the forest has a good service because they provide shadow and they provide also the evapotranspiration. So, and how we calculate and we end up with these maps. So you get all the climatological data like temperature, solar radiation, wind speed, and other meteorological data. And then we use vegetation parameters like what's the vegetation height, what is the leaf area index, that is the amount of greening, the trees, the leaves, and then we model this, and we have a result here is a map that is considered only the vegetation part. But the vegetation part, of course, we don't have all the Berlin in this as a vegetation part. So we get this vegetated ET evapotranspiration, and we correct by the land cover that we use the vegetation fraction to take from this completely vegetation map the areas where is impervious, where there is sealed surface concretes and so on. Then we have the result of how is the map of evapotranspiration in the whole city consider the vegetation areas. So then we can go and calculate this index of greening, the shadows and so on. And this part here, and where is the remote sensing in all of this? But the remote sense, so these parameters here, the vegetation parameter and the land cover parameters we get from remote sense products. So one of the products, for instance, is the leaf area index, that is this thickener of the vegetation part, that is a global product that has for entire plant from 300 meters. So but we can see like here, especially in Berlin, that is the areas around the lakes, and some areas that is far higher the LAI, but we also have these satellites passing and this product giving every 10 days how is the leaf area index. So we can have these trends of how is the vegetation reacting according in the year. So we have the phenological response of the vegetation. So here we get this from the optical sensor, the passive sensors that capture the leaf pigment, the chlorophyll, capture the structure of the canopy, like LAI is a bit the structure too. So every kind of surface has one signature, and this signature depends on where is this wavelengths that's more important. For example, here you can have LAI, here we can have chlorophyll. So depending on the areas or the satellite types, we can get different parameters. For example, another parameter that is a different kind of satellite is to get the vegetation high. So here we have a product for a whole globe from 2020. But this is more smaller resolution. We have 10 meters, so we can have here, for instance, a much fine definition of the vegetation high in in Berlin. So here is around the Stiglitz. So, but this is a passive, active sensor, is a LiDAR that so the satellite send laser sign, receive back, and then depending on the sign, you can define what's the height of the vegetation, and you can have like 3D maps of buildings, of vegetation, and so on. And other important technology is the thermal sensor, so you can have also the temperature, land surface temperature. For instance, here we got from drones in Stiglitz. Stenka, that's here, she did this image. And so you can see that here, where there is tree, the temperature is lower. Where is the house and there is a car here, the temperature is high, and the grassland is in between of the two. So then if you have this kind of image, you can have for the whole city, and you know where is the hot spot. And so as was one of the questions, which kind of satellite to choose, all the time we have to think about the spectral signal, or what is the spectral is more important region for my research, or what the features, the temporal and the spatial pattern. So we have to consider all these three-dimensional, spatial, temporal, and spectral domain. But nowadays, for instance, these maps that I will show with TT, all the data is open access, is open, so you don't need to buy any data, but you only use the data available. So this was what I have to speak. Thank you very much.
Thank you, Albi. Now I would like to invite Dr. Cláudia Guimarães Steinecke. The title of her presentation is Bridging Plant Biodiversity and Remote Sensing Research. Dr. Guimarães is a postdoc fellow at the Remote Sensing Center of Earth Research of the University of Leipzig. In her PhD, she investigated the temporal dynamics of biodiversity ecosystems functioning relationships, such as biomass production and thermal regulation, using terrestrial laser scanning in grasslands communities. Confronting the climate change, she is currently working on how biodiversity interacts with the climate and how these interactions can be affected by extreme events such as drought in temperate forests. Let's get Cláudia now on the screen. Cláudia, the floor is yours.
Hello, everybody. Thank you so much. Can you listen to me?
Yes, we can hear you very well.
Okay, great. So Good afternoon, everybody. Firstly, I would like to apologize that I could not come and be with you today, but I am definitely very excited to show what we are doing in Leipzig. So I am postdoc in remote sensing and geo and ecosystem research at the University of Leipzig. It belongs to the Remote Sensing for Earth Center. And today I would like to show you our work actually tries to bridge plant diversity remote sensing research. So let's start. Here is okay, great. So this is just like just a one plot that we can get from LiDAR. So the hyperlaser scanning is like 3D model of our plots, and I will start to show you what we are currently doing and trying to investigate. So our group actually is pretty much interested in this, understanding the fact within all the ecosystems. So we have here many phenomena that are connected to each other. So we have here all the land atmosphere exchange, for instance, everything that is related to cloud formation or plants that some kind of volatile organic compounds that are key factors of formations. And the albedo, which is actually the reflectance from surface landscapes are not over, for instance, oxygenation, and you attribute an increase on climate extremes such as rain, waves, and droughts. And all these extreme events, they have been seen this in our research that they influence strongly biodiversity in level. So it's not only changing or losing species, they are kind of fact traits. So the function of the species at the ecosystem level, they change the structure, the landscape where they are, and very important as well. So geodiversity, so the soil that supports all this. And with this, the change is directly the existing functions actually that are important to drive all our ecosystems, for instance, carbon storage, water storage, resilience to disturbances. And often talk here that all these mechanisms, they influence and they impact strongly ecosystem service. And ecosystem service, I mentioned here that all the functions of organisms relate directly to also human beings, so like pollination, food production, water flow, so everything so influences us. We are in this cycle, in this effect. So we are trying to understand this and use remote sensing technology. So we have seen that the extreme events have increasing their frequencies, and that's why now we have this Bridging Nature initiative. It's really looking forward to and to predict how the ecosystems will be behaving, so, and also diversity to this climate extreme events. So how can we do that actually? We have great challenges to serve this in global scales to characterize all these systems, and they have multiple spatial scales, and we have to consider also their temporal variability. And if we are looking to it, all that we have different species with different roles and functions, and they represent to count for their presence. So what our group is doing at the moment, we have different approaches, which comes from using satellite imagery for this proposal, but also, and particularly at my work, we are looking at the local level. How can we use proximal sensing to answer those questions? So, for instance, we have different sensors here like as you can see on your top right side of your screen, we have the spectrometer. We have like on the bottom part of the right side, you have the astral laser scanning, like using drones with different kind of cameras, like thermal cameras, as Albitis making, but also RGB information, which derives some colors on the optical information. And also we have here measurements directly on information and, for instance, the chlorophyll content and the varying index. So from our group in work, we have Professor Hannes Feilhauer, which tries to his partner, he tries to identify species from airborne hyperspectral sensors, identify where are the species occurring, how can we understand any effect of disturbances on the ecosystems. So one technique was to find out species combining hyperspectral signal for that. Another example that I think is work from Dr. Tia, one is Salim Sotomanis, a PhD student, where they try to combine remote sensing techniques and also artificial intelligence. Very important science data or pictures that people go with their hands and take pictures of trees, flowers, or animals, and they try to identify, to predict, not to detect species occurrence. So they combine data from people, data from drones, and the map where they occur very precisely. They try to show where they occur in a way that can have not only a question of monitoring and observation question, but also, for instance, any effect of disturbance and these ecosystems. So, talking to my research, I'm very focused on this diversity functioning research and their relationship. I have seen the last few decades that diversity is and enhances ecosystem. And here I say functions because it's not only biomass production, which is the most studied ecosystem functions that we know, so, but also other ecosystems like water capture and soil carbon and temperature regulation. This is important functions that systems can provide, and is definitely driven by biodiversity. So in biodiversity itself, many places, it's not only the amount of species or number of species, but we have this functional differences, positional differences, which is necessary to. And this is actually mostly what I am doing. I will give you some examples here. I am focused on grassland ecosystems because they actually cover around 40% of the Earth's surface, and they have plenty of pictures such as life forms. They can be annual, can measure them in different time and spatial scale. And they also, if you look at very small scale, they are actually considered hotspots. So in my work, I have been for the last years working at the Vienna experiment, which is a German biodiversity system experiment, one of the long term, it's already 20 years, where people manipulate the number and function of species to understand their effects on ecosystem function. And one of my work here was to understand how diversity and buffer can help communities to regulate their thermal environment, their microclimate, and we have seen that in species they can do that, but they depend very much on the configuration of their structure. So that's why we use astral laser scanning here to have very precise information of canopy. So it's like 2 millimeters resolution, and I don't need to destroy my sample to estimate biomass and calculate volume from this data, which helps us to have like information. And what we found here is that species that are close to the ground in a very dense canopy, they are warmer, And the species that they can have like taller and close to the atmosphere that they couple better. They have their surface a little cooler than the bottom part. You know? So, but these species are on the bottom, if they have such a configuration like the curvy one, no? So they are in these clusters, they can also be very cooler. So it's really a fine description of the species. And this is one study that happened with grassland, and now I am focused. So we also running other projects look into the tree diversity, but then in this case, I'm using leaf traits, so information about the leaf, how much water they have in their tissue. And for that, I use also a proximal sensing using my test based on their reflectance. Reflectance, you can see how much water they have inside. So lower the reflectance, higher is the amount of water. And this is the opposite for deep. And then we can really estimate, how much reflectance only for the cloud part here is really the leaves, the yellow one, the green one, are the trunks that are actually not full of water, so we can retrieve such a data. And this is also something that depends in biodiversity research. We also use some kind of actions, leaf angles that help us to understand how plants move their leaves of along the way because of the lack of water. It's also something that is possible to do, and it's easy to manipulate this. We needed to have to read this, something that reflects physiological patterns of communities. So now I just wanted to show you something as a message also from my side. Remote sensing is very male-dominant research, but I just want to highlight that we have plenty of women working on this. And if you are on Twitter, you can also see them, pages of Landsat, dates of drones, women of waveforms, and sister of stars from different backgrounds among the globe. And they are providing a lot of data and showing how can we also develop this field of work, which is actually one of my inspiration of my research. So with this, I thank you for your attention and happy to answer any questions.
Thank you. Thank you very much, Claudia. We had some issues with the connection, but I think with the slides, I think also it was very, very clear.
Sorry.
No issues. Let's move to Q&A. So questions from the audience. Who will be the icebreaker? You again? No pressure. We have their question.
Hi, nice talk and really interesting. I like the names of drones. What kind of operational applications would you find for your work? Maybe commercial or non-commercial end users of this kind of science. Thank you. To Claudia.
I'm sorry, I didn't hear you correctly. Could you please repeat?
Yeah, sure. What kind of applications or operational uses would there be for your science and your this kind of small scale work?
Okay, so can I answer directly? So let's just go, because like what we are doing using terrestrial laser scanning or any hyperspectral image, we are trying to show how much the biodiversity of ecosystems they influence ecosystem function. So for instance, biomass production is one of the most important. For instance, we can see that different species, they enhance the productivity. So if you are, for instance, in a field any sward, and you have different species of plants there, they will produce much more biomass than monoculture, for instance. So this is the idea behind all this this biodiversity research, and this is also being applied also on agriculture sector, but also it's hard to for them, also for this sector, to understand that we need to have some kind of different species working on these systems to improve our productivity. And we are trying to show that not only from remote sensing techniques, but from studies directly, like this experiment that we have in Vienna, that this works and should be applied. This is mostly the application of that.
Thank you, Claudia. More questions? Here.
I have the question for the first speaker. So I thank for your coding service, or I couldn't remember the whole name, and that's really cool. And I'm kind of curious what could be the possible countermeasures according to your service results, like you estimate the ET index for the urban area. Let's say we observe the central Berlin is kind of overheated at the moment. So what could be the next step that we can deal with that? I'm kind of curious. Thank you.
Thank you for the question. We did some detail maps, that hourly map for the entire city, so we can see which areas of the city is more likely to have low thermal comfort. So can have different techniques from green roofs or some from trying to do some concepts like sponge seats or find some natural solutions to increase the vegetation in these areas to improve this thermal comfort. And now we are trying to relate this with the social aspect, and with to see if the areas that has more heat waves, more heat islands, are the ones that has less people with less income, or because you can observe sometimes in the surround you have more vegetation, but you have like this some areas very dense of the city, you don't have so much vegetation. So how this play with the social justice too, but then trying to encourage the urban planners to think this together and bring an urban environment a bit more suitable for the future.
Thank you very much.
We have time for the last question.
Thank you so much for your very interesting presentations. I have a question to Dr. Rocha. You know, Berlin is planning to install a lot of solar panels on its roofs. And on your opinion, what will happen with the temperature within a city if the city will start on each single building to have its solar panels and probably start to produce food also inside the city within of different biotechnological products? You know, what will happen? You know, how our ecosystem within a city possibly will change? Thank you for your answer.
Yeah, all the interventions maybe has some side effects. We never know precisely, but of course you have like, if you still produce energy with solar panel, that is more sustainable. But if you have a lot of air conditioners or a lot of things that provoke heat, sensed heat, you will still increase the temperature and only artificially going down. So I'm very for natural solution, or to have more green space, to have more the surface not so previous, more this sponge concept, more reduce the water that go to the drainage system and go to the river, but don't penetrate in the soil, don't get the whole water cycle and so on. So yeah, you have to sometimes not only technology solutions, but you have to balance with natural solutions to have even not only about the temperature, but even about to the human being feel a bit better in an environment with more vegetation, more green areas, and more balance than nowadays with a lot of concrete, steams and grasses.
Thank you, Albi. Thank you for the questions. I know there were some more questions, but I hope you can use the time afterwards during our cocktail for interaction. So I would like to thank Albi and Claudia again for the great panel. Thank you very much. And now to conclude our event, I have the honor to welcome directly from São José dos Campos in the state of São Paulo in Brazil, Professor Dr. Evelyn Leão de Moraes Novo. Dr. Evelyn Novo is a senior researcher at the Earth Observation Division in the Brazilian Institute for Space Research, INPE, under the Ministry of Science, Technology and Innovation of Brazil. She has over 30 years of experience in developing and applying Earth observation satellites on integrated studies of the Brazilian Amazon. She participated as the Brazilian principal investigator in the large-scale biosphere-atmosphere project called Linking Remote Sensing of Variations in Inundation and Aquatic Vegetation with Regional Analysis of Carbon Dynamics in Amazon Wetlands, among many other projects. So we are very honored to have Professor Evelyn with us today. Professor, the floor is yours. Professor, can you hear us? Professor? We are calling her. Is joining? Maybe she got the wrong link.
Sorry.
Okay, now you have.
Okay. Why don't you in? Okay. Okay. First of all, I would like to thank you for inviting me. Can you hear me?
We can hear you very well.
Okay, I would like to thank you for inviting me for this. Oh, you want me to introduce me or not?
I already introduced you, Professor.
Okay, so, okay, the evolution of, I'm going to talk about the evolution of remote sensing since the 1970s and the contributions from Brazil. And I would like to thank first Igor Asha for inviting me. He was a former student that now works in Germany. And also to Sylvia and the Brazilian embassy in Berlin for being able to participate in such a nice night's meeting. First of all, I focus my presentation in 4 topics. First, I will talk about the decadal advances in remote sensing science and technology and how we profit from them. After, I will talk about the main remote sensing applications contributions from Brazil, the new applications of remote sensors for monitoring inland waters, which is my subject, and I went with some concluding remarks. Well, I will talk about these last 50 years of remote sensing science and technology advances in Brazil, because I kind of witnessed most of these advances, because I started studying at INPE in 1974, where I developed my master's degree to work with the first Earth research satellites launched in 1972. At that time, INPE was quite ahead in the space science and space technology advances. Brazil was the 3rd country in the world receiving, processing, distributing, and developing Landsat data applications. And I was part of a project that was able to prove that very poor resolution 4-band images called multispectral scanner system, MESS Landsat 1 images, were able to detect and measure deforestation rates in Brazil, although there was no conditions yet at that time to develop a operational program or operational product that could be used for estimate annual rates of deforestation. It took more than a decade for us to have the development, technological development, knowledge development to make a science, remote sensing science of going to the field and doing things to try to help to define this new to use this new information for practical purpose. In 1984, the TM Landsat was launched, and it was very useful because the spatial resolution of the MESS was very poor, dropped to 30 meters, and the number of wave bands also increased. So in 1988, INPE has started his program for monitoring annual deforestation rates fraud. The 90s was the decade of SAR satellite advancements, and it was very expected for Brazil because, as being a tropical country, most of the problems in monitoring deforestation or using remote sensing and Landsat optical remote sensing for studying Amazonian ecosystems was the high cloud cover. So SAR image looked as an opportunity to increase the revisiting time and the ability to get more information on Earth surface. And then in 2000 years, from the 90s towards 2000, there was a paradigm shift because the climate change signs had been being spread all over, and scientists were very aware on the need of studying the relationship between climate system variables and how these variables interacted with the land surface, land cover, ecosystem process, etc. And then at that time, INPE NASA had a very nice project, which was the INPE NASA LBA program, with many projects on biodiversity, ecosystems functioning, wetlands functioning, etc., that allowed an unprecedented knowledge of the Amazon basin role in the regulation of Earth climate. And then in the decade to 10,000, we have from 2014 on the ability to have much higher spatial resolution instruments that allow for studying cities, classifying, looking up to urban vegetation, etc. So it's kind of a very important breakthrough also in the technology and the science of remote sensing. And finally, in the 20s, in the end of the 10th and the beginning of the 20s, we start in the middle of these 2 decades, we started the satellite constellation approach. That's a way of using very many platforms, many satellites, to increase as an option to increase the frequency of information, so as we can assess time trends in the Earth's surface. Okay, and then given this broad aspect of the remote sensing, the main remote sensing at INPE, I'm gonna talk a little bit what I think its most relevant contribution regarding remote sensing applications. First is the INPE 988 INPE started project to monitor clear-cut deforestation in the legal Amazon and produce annual deforestation rates as part of the Amazon monitoring program. In 2004, INPE established the free access policy of deforestation data and cyber satellite image, which resulted in the distribution of over 120,000 Chinese Brazilian satellite images between May 2004 and July 2005. This policy is still on, and it is responsible for creating a very rich remote sensing community and enterprise, which are making a lot of progress in that area. And also this move, the INPE's move towards releasing the image, making the image free, we could have this also. There is this movie in other image providers like NASA, U.S. Geological Survey, USGS, U.S. Geological Survey, etc. And in 2013, he implemented the instrumentation laboratory for aquatic system, aiming to develop operational products for monitoring inland aquatic systems which culminated with the first efforts in proposing a new Brazilian satellite program for water quality and water resource management to meet Brazilian Water Agency needs. Also, it's a very important, in my view, this move, IMPS move. And also, another large contribution of the IPS to society is the long-living graduate program in remote sensing, which has been responsible for preparing human research for remote sensing science, image processing tools, geoinformatics, that made it possible to give access to remote sensing data, but in public information to Brazilian society. So the IMPS Amazon Monitoring Program is composed of DETER, PRODES, fires monitoring, Terra class, and more information you can find in the link. And the PRODES is able to detect in a yearly basis the deforestation rate. So we can have the deforestation rate every year. And this information is used to be very useful for driving public policies. Besides the deforestation project, there is another very important project within the Amazon monitoring program, which is the DETER project, which is an alert system that is sent almost every day to the environmental agencies, so as they can send people to control and to inhibit the deforestation. So this system, together with PRODES, are very useful systems, and they have been working for the last 20 years or more. And last year, here we can see how the DETER acts in relation to DETER is important to as a way to restrain deforestation. As you can see, it was PRODES 2018, and in 2009, this area has no deforestation. Then we could look at in May 2019 an area of deforestation. And if you look at the very high resolution image, which is the planet image, this image can be, this area, deforested area, can also be observed. And if we go further and further, we can see that there is not very much difference between what we can see as a deforested area in the Landsat system and in the planet very high resolution images. And what happened here, what we can see is that by ignoring the sending the enforcement to prevent deforestation, there was an increase of about 88 square kilometers in the deforestation. So the DETER project is a very important instrument for providing new information and for in this policy for controlling deforestation in Brazil. And then another area which we are working together in the Amazon is that for the last, let's say, for the last 30 years or more, there has been an increase in the anthropogenic impacts, which degrades water clarity in the Amazon River. So we are developing a tool which is taking advantage of the long-term time series of Landsat image to monitor SEC disk depth changes a long time in different stretches of the Amazon floodplain, lakes, and rivers. So we have here areas where these red dots are the areas where we have been working, Lago Uruguai, Tapajós River, Monte Alegre Lago, Madeira River, Solimões River, Negro River, and as study areas. And what we used was TM, ETM plus, and OLI images, and in situ simulated remote sensing reflectance and SEC disk depth provided by the Brazilian Water Agency, ANA. And these images, this data were used to train the algorithm, and there were many ways, many different algorithms training, support vector regression, MEDN, random forest, and the algorithms were evaluated using Monte Carlo simulating and were validated with Landsat collection level 2, remote sense reflectance, used matchup of in situ data for ±5 days. And then this best algorithm was chosen to assess time changes in SEC depth. And then I show some of the results. The model validation with satellite data show that there is a quite good agreement between the SEC depth model SEC depth and measured SEC depth. And also, we also worked with these time trains from 1985 to 2002 to see how these SEC depth traits behaved along this time span. And one thing that, one of the things we could detect was the effect of dam construction on SEC depth time ranges. As you see here, the SEC depth increased from 985 towards 2022. And this increase is in agreement with the analysis carried out by Lee et al. And it's related to dam construction in the Madeira River. As we can see here, we have two big dams in the Madeira River, and it's thought that this, it's known from limnology that these dams, they retain sediments and they increase the amount of sediments that were sent towards downstream the river. And one is the downstream, there is this Santo Antonio hydroelectric power plant. And here we have also another power plant here, Jirau power plant in this, and here at this, another aspect that we analyzed is the effect of illegal gold mining. And we observe that despite this very red line shows that is up and down in the trends of SEC depth along the time. But if you look at the trend, time trend here, we can see that the trend is of increasing SEC depth. And this trend is related to gold mining in the Tapajós River. And this trend was confirmed by a previous work carried out by Lobo et al., where we can see that there is a very tiny relationship between the gold price change, the gold production, and the AGSM, or the area of gold mining, a long time. So when we look back to this, when we look back at the trends, we see that there is this decrease in SEC depth during the time where there is a decrease in gold mining activity. So these trends are related to the gold mining activity. And another area we are working at is assessing river lake connectivity based on superdome planet images. And also, this superdome application is a way of assessing automatically using just the spectrum and the color of images to connect, to assess if there is a connection between a river and a lake, a floodplain lake, because this connection would affect fish productivity, fish biodiversity, and it is a very important information in an environment of climate change, because the water levels change up and down without so much respect for the nature and for the people who live from the fisheries. So by knowing the connectivity among this data, and know if this connectivity is changing and how they are changing, we can promote public policies to try to help the riverine population to cope with those anomalies. So by using this by using these anomalies, we can see here that when they use the SAN spectral angle mapper, you can compare the reference spectrum with different water colors. You observe changes in water color and analyze those changes and group and measure these differences to classify, to define if the lake is connected or disconnected.
Professor, sorry, Professor, can you hear me?
You can see more information in Paulino et al. 2002. And this information, reference spectrum, lake sand, minimum sand for dating lake, area difference, water level estimated from cyrometry, that altogether a classifier, and this non-connectivity, which is also defined by visual interpretation, and the feature SAN, area difference spectral response water level, this information allows to model and to define which are the connected lakes and which are not. And by using this model, we could have this following results from 21 lakes which were not connected, which are connected, which are not connected, only 5 were classified wrongly, and among 36 lakes which were connected, only 5 were wrongly classified. This project is a going-on project which are still being finished yet. We haven't finished yet. It's not ready yet for to become operational. And it is, we acknowledge the funding from Saberes project and PNB Paribas Foundation within its call on climate and biodiversity initiatives, because the river lake connectivity acts upon phytoplankton biodiversity and also on fisheries biodiversity. I will conclude this presentation. My concluding remarks are, which science grows with human biodiversity as well, with the courage of young scientists to challenge the present knowledge, with the respect for the senior scientists that acts as a bridge, help to open the incredible path where the new knowledge is still to be assessed. So I'm very happy to be here, because I can see that remote sensing after half a century is still a very driving area where there is so much to be learned, and I learned very much today with this new generation that's coming and doing well. And I think you are quite important, because this is a very tricky moment, and I think that we need to look at the Amazon with sorrow eyes nowadays. And because if it goes as it is now, it won't only be an awful environment for the Amazon and for the people who live there outside the business, and for the world as a whole. So I hope you pay attention, because we can see it better with remote sensing. And through my lifetime, I could see that remote sensing revealed many inconvenient truths about human behavior and how we manage the environment. Thank you very much.
Professor Evelyn, thank you very much for sharing your large experience with us here, and congratulations for the great career that which you devoted a lot to our space research program. Thank you again very much. With this brilliant presentation, we have now come to the end of our event today. Many thanks to all the presenters here and also online, to the audience as well, and to the organizers of Berlin Science Week 2022. Special thanks to the embassy team who has worked backstage to make this possible. So Silvia, Felipe, Thais, Gaylor, and Ricardo, many thanks. And for those here at the embassy now, we will move to the hall next door, as I said, for some wine, some Amazonian Guaraná, and some snacks. Thank you again. Bye-bye.